Hello, this is a video lesson on radiographic equipment starting with part 14A on waves, electricity, magnetism, and electrical devices. So in this entire part 14, we're going to talk about waves and the inverse square law, laws of electrostatics and magnetism, types of materials, factors in the electrical circuit, the electric current, generator and motor, the transformers, and rectification. In part B, we'll talk about the electric circuit and generators. In part C, we'll talk about the X-ray tube. In part D, we'll talk about X-ray, specifically factors that affect beam quantity and quality, as well as subject factors. So let's begin with part A. In part A, we're going to start by talking about the cycle. The cycle is otherwise known as a wave, and the wave has two pulses. It has a positive pulse and a negative pulse. So in one cycle, you have two pulses. In the United States, we have 60 cycles per second of frequency. 60 cycles per second. So when we look at frequency and wavelength, frequency is the number of cycles that we have per second. So in the first example, this is oops, let me change colors here. From here to here is one cycle, and from this would be A, and this would be B, and then from B to C is a second cycle. So that's we have two cycles. So 2 cycles per second, but look at the wavelength, it's really long. So lambda is the symbol for wavelength. And then in the second example, we have a total of 4 cycles going across here in this 1 second, but our wavelength is now shorter. So when we have a lower frequency, we have a longer wavelength, and we have a higher frequency, we have a shorter wavelength. So looking at the equation for that, velocity equals frequency times wavelength. Velocity doesn't change with electromagnetic radiation. It doesn't change. So as frequency goes up, wavelength has to go down. And that means that they're inversely proportional, which is exactly what we just said in the previous slide. If you have a high frequency, you have a short wavelength. And wavelength, just to restate, kind of like review what that means, it's distance from crest to crest. Distance from crest to crest. And so that's exactly what we're looking at, these wavelengths here are the values from crest to crest. The inverse square law, intensity is inversely proportional to the square of the distance. And here's our formula. I1 over I2 equals D2 squared over D1 squared. And Bouchon's just showing a picture of him sitting at 1 meter, which is like a yardstick away from a light bulb, and that he can see fine. But at 3 meters, he's having trouble seeing. So it's just that as you increase distance, we decrease radiation intensity. So as we increase distance, and that makes distance our best friend in radiology, we're going to decrease radiation intensity. We're going to decrease it by a squared effect, which is really important for us. That's why distance is the most important cardinal principle. So laws of electrostatics and magnetism. So we have like charges repel, unlike charges attract. We have Coulomb's law, that with an increase in the strength of charges will increase repulsion or attraction. An increase in distance between charged objects will decrease their repulsion or attraction by a factor of 2. That's called the inverse square law again. Electric charges are concentrated along the sharpest curvature of a surface. Excess charges reside only in external surfaces of conductors, meaning on the outside. That's because electrons are in electron shells and protons are inside the nucleus and they cannot move. So only negative charges, which are electrons, can move along conductors. Laws of magnetism, like poles repel and unlike poles attract. In the magnetic force or Maxwell's field theory, it's a lot like Coulomb's law, except we're talking about magnetism here. So an increase in strength of magnetism will increase repulsion or attraction. An increase in distance between two magnets will decrease the repulsion or attraction by the factor of 2, going back to the inverse square law. Magnetism is stronger at the poles of a magnet. The magnet has two poles, which are north and south, called magnetic dipoles. And if you break a magnet, it results in each fragment becoming a baby magnet. Here's the process of looking at the inverse square law, that if we have two objects that are close together and then we increase them by a factor of 2, that'll decrease the intensity by 1/4. And if we increase it by 3 times, we're going to decrease the intensity by 1/9. So if we increase distance, we're going to decrease attraction repulsion by 4 times. If we increase distance by a factor of 3, we'll decrease the attraction repulsion 9 times. And because we always have to square the distance, and if we increase distance by a factor of 4, we'll decrease the repulsion attraction by 16 times, and so forth. Then we have types of materials. Superconductors allow flow without resistance, like titanium and niobium. It has to be very, very cold to do so, though. Conductors allow flow of electrons in both directions, and that's like copper and aluminum. We use copper for wiring in homes very commonly. Insulators inhibits the flow of electrons. That'll stop the flow, and that's why we cover our copper. So this is the copper in this example, and there's the rubber down here at the bottom. So rubber is going to be coating electrical wires. And then semiconductors, this is a semiconductor here, which is a solid state diode. That's your rectifier. Allows current to flow in only one direction. And that rectifier is comprised of silicon. Now we have magnetic materials. Ferromagnetic materials are strongly attracted to a magnet, like iron, nickel, and cobalt. Paramagnetic materials are weakly attracted. There's the gadolinium that we use in MRI. So we want to have something that's weakly attracted to a magnet, not strongly. Ferro, by the way, means iron, so that's why it's strongly attracted. Non-magnetic is not attracted to a magnet, so that would be wood, glass, rubber, and plastic. Diamagnetic is weakly repelled by a magnet, so that would be lead, water, beryllium, and bismuth. So now factors in electric circuits. So we have the symbols for electric potential, which is V for volt or voltage. Current is the I, ampere, and resistance is the R, which is the ohm. The other terms for electric potential are important for us to know. So you have to know that there's also potential difference, voltage, and EMF. EMF stands for electromotive force. So again, we have potential difference, voltage, electromotive force, and electric potential. Ohm's triangle is where we have V equals I times R, so we put the V on top, and we have the current down here on the left and the resistance on the right. Just like the mass triangle, we have a V equals I times R triangle. PIV, we have P equals I times V, so P stands for power, which is the unit is the watt. Current is the I, so that's the ampere, and V is voltage, otherwise called electric potential, potential difference, or electromotive force, and that is the volt. So we also have the power loss formula, P equals I squared R. That's another formula for power loss. Alternating current is where electrons oscillate back and forth, meaning that they go in a positive direction and a negative direction. So it's going in both directions, which is positive and negative. It's a sine wave, otherwise called a cycle. In this case, would be one cycle we're looking at. And we would example, if you wanted to plug an electrical appliance into a wall socket, that would be how you're using alternating current. You plug your laptop in, you're using alternating current. Direct current is where electrons flow in one direction. Now we have two types of direct current. We have steady direct current, which is the one type, where current voltage is the same, it doesn't change. And then we have pulsating DC, where the current pulsates. So it's only going in a positive direction. In both cases, there's no negative pulses, in only one direction, which is positive. The example of a steady DC would be from a battery, and the X-ray tube operates on pulsating DC. So to look at the difference between a helix, a solenoid, and an electromagnet. A helix is a coil of wire. A solenoid is a helix, which is a coil of wire, that orange thing, that carries an electric current. The electromagnet is a solenoid with an iron core. So the only difference between the three of them is that each one has an iron core. What they all have in common is the iron core, but the solenoid has the electric current, where the electromagnet has an iron core and it has the electric current. In the right-hand rule, which is Fleming's rule, the thumb, if we hold something in our right hand and we put our thumb up, the electric current is going to go in the direction of the thumb, and the magnetic field is going in the direction of the fingers. So looking at the direction of the fingers. If you look down from the top down, it'll be going counterclockwise. So going counterclockwise, looking at this. Now we have symbols and some different types of electric circuit elements. We have the resistor, and the resistor symbol is the squiggly line. It inhibits the flow of electrons. The battery has got a symbol with several lines that used to be called the voltaic pile. It provides electric potential, which is voltage. The capacitor is going to store electric charge, and the unit for capacitance is the farad. The transformer is going to increase or decrease voltage by a fixed amount. It only operates with alternating current. And here's the solid state diode, which is made up of a semiconductor, and that specifically silicon allows electrons to flow in one direction, which is what a semiconductor does. And so that is a rectifier. A generator is going to be a device that converts mechanical energy to electrical energy. So it's going to, as you turn the armature with a generator, you're going to apply that rotation, and that rotation that they're showing here in this is going to result in alternating current, because it either has a slip ring or no slip ring, and that's going to result in alternating current. If instead you put a commutator ring, the commutator ring is going to result in pulsating direct current, and that's the result on this one. A motor is something you would plug in, so you want to have electrical energy. We're going to make it the example would be to blend something where you have blades, and those blades are going to turn, so electrical to mechanical. The other example is the induction motor in the X-ray tube. What is a transformer? It increases or decreases voltage and only operates with alternating current. We're going to talk about three types of transformers. The step-up transformer, which is the first one at the top. We have the step-down transformer, which is the second one. And then we have the auto transformer, which is the third one. So looking at the transformers, the step-up and step-down both have two coils of wire. They have a changing current, or AC, in the primary coil that causes a changing current, or AC, in the secondary current in the coil. So they operate on mutual induction. Both of them operate on mutual induction. A step-up transformer steps up or increases voltage. The secondary coil has more turns than the primary. This example has 20 turns in the primary and only 5 on the secondary, and only 5 on the primary. The turns ratio is always greater than 1. Turns ratio is NS over NP. So if we were to calculate the NS over NP for this one, we would take 20 divided by 5, and that number would be 4. So it has a turns ratio greater than 1. In the step-down transformer, it's going to step down or decrease voltage. The primary coil has more turns, and in this case it has 50 turns compared to 10 on the secondary side, and the turns ratio is less than 1. So again, using the turns ratio formula, we would take 10 divided by 50 in this case, and we would get a value of 0.2, and that is less than 1. Notice in the case of a step-up transformer that we're increasing voltage. So it increases voltage, it increases the number of turns are increasing, which is N, and we're going to decrease the current. So P equals I times V, which is our formula for power, and since that is true, as current goes up or voltage goes up, one of the two, the other opposite one goes down. So voltage goes up, number of turns goes up, the current goes down. In the step-down transformer, our voltage goes down. It went from 1,000 down to 20. Our number of turns decreased. They went from 50 to 10, but our current went from 2 to 10, so our current went up. So that's just looking at what happens within with step-up and step-down transformers. In the auto transformer, it only has one coil wire. It operates on self-induction, and the auto transformer selects voltage. It's called a variable transformer, otherwise called a variac. A variable transformer or a variac. So the high voltage transformer is called a step-up transformer. Its purpose is to change volts to kilovolts and changes amps to milliamps in our X-ray circuit. So we're going to be increasing voltage and decreasing current. The second transformer that we use in our X-ray circuit is the filament transformer. That's a step-down transformer, and its purpose is to heat the filament. Since we increase current, that's going to increase heat. The third transformer that we use is the auto transformer, and that's it's the variable transformer. We're going to use it as a step-down transformer in our circuit, but it selects voltage. We have four types of transformers by construction. The first one is called the air core. The air core is just two coils of wire lying side by side. This happens to be a step-up transformer, but you can see that there's just wire. In the open core, which is the second one by design, it had a lot of leakage, flux, and power loss just like the air core did. And it has two iron cores that are inside the coils of wire, and they're going to be just a little bit better designed than the air core. The closed core, which is the third one, can be a square, a rectangle, or a circle, but it's going to be entirely closed so that there is a gap that's going to be closed. So we can see that in these first three that we can tell that this is a step-up transformer in the first one. In the second one, we've got a step-down transformer. In the third, we can see we have a step-down transformer. But the point is I wanted to bring up is that in the shell type, which is the last one, we cannot tell. The windings of the step-up side and the step-down side, the primary and secondary sides, are wound around the center, so we cannot tell. And that's made up of silicon. That's something that's different. So the open core and closed core are comprised of iron. The shell type is comprised of silicon steel. So we have three types of power loss. We have I squared R losses, which is the formula for power loss, P equals I squared R. They're also called copper losses. They include mainly the loss of electrical power due to the resistance of the coils, and power loss is just directly proportional to the square of the current. Loss of power is given off as heat. The second second type of power loss are eddy current losses. These are, this is an example of a closed core transformer that we're looking at here, and it's showing the swirling currents within the core caused by alternating magnetic flux. The third type are hysteresis losses, and that's with rearrangement of the magnetic domains, how they arrange themselves while we're using them. It results in power loss also. Rectification is our final topic for this section, and that is where we have the process of converting alternating current to pulsating direct current. So before the rectifier, we have the positive and negative pulses. So positive and negative, but after the rectifier, we only have positive. So that's the concept of a process of rectification, is converting alternating current to pulsating direct current. What's going to accomplish that is going to be a solid state diode, and this is again the symbol for it. Electron flows opposite the arrow, and so this is the electron flow that we're looking at down here. The device that actually changes AC to pulsating DC is called a rectifier. And again, this specific type of rectifier is a solid state diode. So we have two types of rectification. We have half-wave rectification, which was the very first type. We still have AC that's changed to pulsating DC, but we're only going to have one pulse in a cycle. So this is a cycle here from this point to this point, and we only have one pulse. And so how we get there is we can do it with self-rectification, where we have no rectifiers. The problem is we have reversal of electron flow, where the electrons usually go from cathode to anode, but they're going to try to go backwards. And that's called inverse voltage. They're going to try to go backwards from the cathode anode to the cathode, and that causes the tube failure. So we really would prefer not to have self-rectification. The other option is to have one or two rectifiers. This is showing one rectifier, which will be fine. But back in the time that we had half-wave rectification, they had what were called valve tube rectifiers. And so they had two rectifiers just in case one stopped working, it took over the job of the one that had malfunctioned. So we could have 0, 1, or 2 rectifiers with half-wave rectification. And then we have full wave rectification, which is where AC is changed to pulsating DC. In this case, we're going to go from alternating again, but this time we're going to use 4 rectifiers. These are the rectifiers, the solid state diodes made up of silicon. And we're going to then change the negative pulses are going to move up to positive. We're going to change negative to positive pulses. So we have 2 pulses per cycle now. So we start off with, if this is a alternating current, after full wave rectification, we would have 2 pulses. And that's why it's called full wave rectification, because we have 2 pulses in one cycle. And this concludes our first lesson on radiographic equipment. Have a great day.